So here, there is this rope that's wrapped around this pulley, and then there's a weight hanging off the end. And so this is falling down. They want to know the tension in the rope, and they want to know the acceleration at which the hook falls, and the angular acceleration of the pulley. Now remember, in the past, whenever we dealt with pulleys, it always says massless, frictionless. Okay, because if the pulley has no mass, then it requires no energy to turn it. Okay, but in reality, that's not how it works, because you know that things with rotational inertia, and that affects how easily it spins. We saw that with the plastic hoop and the wood disc. Remember that? Okay, so then the question is, how do you solve these problems? If you see a problem with the diagram where there's rope and tension, all that stuff, what do you think the first thing you should do? Yeah, do a force diagram. And the first thing I'm going to do is I'm going to say this pulls down with tension on this. There's this radius right there. Well, actually, let me do it over here. There are how many objects in this diagram? Yeah, there are two. So there's going to be like the hook. And the hook has tension and MHG. Does that make sense? Okay, good. And then you have the pulley, right? And the pulley has a radius. It also has a mass of the pulley, and there is also a tension pulling down. Does it make sense that this tension is the same as that tension? Yeah, because there's nothing in between, just there to there. Yeah, their tension still exists. Because the nice thing is when it's frictionless, massless, then the tension is the same throughout the entire system. And when there is mass and there is friction, then you have to do it a little differently. Here, they're just cranking it up one notch by saying there's mass, but they haven't put friction on as well. And all that would happen is the friction would create another torque. But let's go ahead and take a look at this. For this one, what is the sum of the force statements on here? Who's winning? Right? So it's going to be the sum of the forces in the y direction here is equal to what? MHA. Does that make sense to you? Yeah, right? Who wins? Gravity. And then, but do you see this rope is pulling back, slowing it down? So is it going to fall the same as gravity, faster or slower? Does it make sense to you? It's going to go slower than gravity. If you were hanging on this rope and you fell, you would hope that your friends would grab the rope up here and prevent you from falling at the acceleration of gravity. I mean, that's at least your hope, right? So that's kind of like what's happening here. It takes energy to spin this wheel, and that energy is taking up some of the energy that's coming into here. So the sum of the forces in the y is MHA. And then, of course, that means MHG minus T equals MHA. Okay, now, over here, this is not simply a force diagram, because something is doing, what is this wheel doing, this pulley? It's rotating. So what do I need? Instead of a force diagram, this is actually a, what do you call that? What do you call a force with a right angle in it? A torque, right? What do you call a force with a right angle? A force is a straight arrow, right? So if you take that force and bend it 90 degrees, it's a torque. So just think of a torque as a force with a right angle in it. Okay, so we have that torque, which means this isn't a force diagram. This is a torque diagram. So then I need to do the sum of the torques is equal to, and not MA, it's equal to what? What is the corollary for M in rotation? I. And the corollary for A? Alpha. So the sum of the torques is I alpha. And so there's only one torque. That torque is T times R, and that equals I alpha. Now, those two statements we have to blend together. And we can do that with a little bit of whatever magic, sort of. Look at the chapter. On page, is it 254? What is the I for a flat disk or a cylinder? And a flat disk is a cylinder. That means what is the moment of inertia for a pulley? If you look on page 254, you'll see that it's what? If somebody has their book, Shivers, Cole? No? Oh, okay. It is 1/2 mr squared. That is the moment of inertia of a flat disk. So what I get here is I get TR is equal to 1/2 mr squared. And what is alpha? Just like, what is theta? Theta is what over what? Theta is what over what? X over R. Okay? Omega is what over what? V over R. Or you can do theta, you can do delta theta over delta t. That's true, that's not wrong. But you see what I'm getting at? Theta is X over R. Omega is V over R. Alpha is A over R. Do you see why I'm bringing this up? Because what's over here? A. See, now if I do A over R, then this cancels with that. This one cancels with this. And now I can solve these for whatever I want because I get T is equal to MA over 2. Now be careful because what is this M right here? Is that the mass of the hook? No, it's the pulley's mass. That's the pulley. It's the mass of the pulley. But I can now take this, if I want to, and go ahead and say, oh, let's say A is equal to 2T over mass of the pulley. Now I can just plug that in over here. So over here, I have MHG minus T is equal to MH times A. Well, A is 2T over mass of the pulley. And now I can solve this for T. Boom, get my answer. And if we do that, we get MHG minus T equals, well, I guess we could say, you know what, I'm just going to go ahead and move the T over. I'm going to get MH over MP times 2T, whoops, plus T. And that equals that. So now I can factor out the T here. So I get, I won't move it so I don't confuse you. MH equals, and then here I get T times 2 MH over MP plus 1. And now I can solve for T. T is equal to MHG over 2 MH over MP plus 1. And now you can plug all that stuff in and get your answer. What's the hanging mass? Is 1.1 times 10 over 2 times the hanging mass again, which was 1.1, over the mass of the pulley, which was 3.3? Oh, it's just 3? Okay, just 3 plus 1. So this becomes 2.2 divided by 3, which is, what? What is that, like 0.7 maybe? I'm guessing. 0.7 plus 1 is 1.7, so it's 11 divided by 1.7, which is like 6? I don't know. 6.47? Okay, I'm just going to go 6.47. Or even 6.5 newtons. Okay, you must know how to do this. Hint, hint.
So basically, you just have to remember what T equals.
Well, you don't have to remember what T equals. You just have to look in the force diagrams and see, because remember what I told you a long time ago. If you have two things in a problem, then what do you have to look for? Two objects, two people, or the same thing in two different states. What are you supposed to look for? Yeah, you're supposed to look for the bridge. You're supposed to look for what connects. What is the same about those two things? So does it make sense to you that in here we have this hook and this pulley, and the thing that must be the same about the hook and the pulley is the tension in the string, because the string connects the pulley to the hook, and there's nothing in between them, so that the string, the tension at the top of this must be the tension at the bottom. I mean, it's like if you grab one end of a rope and I grab the other end of the rope, and we both pull and nobody wins, what must be true about your tension and my tension? It's got to be the same. Does that make sense? And then in this case, if your tension is this hook pulling down and my tension is the resistance of the pulley, who's going to win? You are. And then, but that's because of the net forces. And that's where the acceleration comes into play.
So we just have to remember there is acceleration because the hook is pulling.
Yeah. So I just do the force diagram like we've always done. I just do the torque diagram in the same manner that we've done the force diagram, and then I do a little conversion magic, and boom, solve the algebra. And this is about as hard as it's going to get. So like on a test, you might see this as multiple sections. Like one sections do this, one sections do that, blah, 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 blah. Yeah.
Now you have inertia down as 1/2 mr squared.
Yeah.
My notes are the sum of mr squared.
Oh, the sum of mr squared is an exact statement. What that means is you're supposed to take the moment of inertia of every particle in that object and then add them all up. When you do that, what you're actually doing for a disk, does it make sense to you? If I take this ooh, the fudge nuts. Okay, whoops. I'm just randomly grabbing things, throwing things around. Does it make sense to you that if I have a disk like this, and I have a center right there, do you see like if I want to pivot this disk, then what I'm doing is like I'm kind of pretending, I'm kind of looking at, if I say that I is equal to the sum of mr squareds, then that means if I divide this into even pieces, whoa.
That's such a
Right? If I divide this into even pieces, then this should just be the moment of inertia of each one of those pieces added up. Now, moment of inertia is easy when it's like a ball on a string, because we count all of the mass at distance r, right? How do you do that here? Right? Do you see like the radius changes? The radius goes anywhere from like whatever 0 to r.
Wait, what? The radius changes?
Yeah. For example, in this section of whatever this is that's rotating, do you see how like I could put these points, and see how every one of those points has a different radius,
Okay.
right? Now, if I take, so I'm not going to do the math for this because I don't think it's necessary. But what I do is, if you are familiar with calculus and limits and all that stuff, basically I take a really thin piece of this, and I say that really thin piece is delta m. And that delta m is equal to the density of that object times the delta area. It's a little piece of the area. So first I say that there's going to be, like, the moment of inertia is going to be the sum of the r squared times delta m. So it's that r radius squared times a little piece of the mass. That little piece of mass, the sum of the r squareds becomes delta a. Right? And then I create a statement that describes delta A. And there's a bunch of junk steps, but it's like take a little piece and then describe that little piece and then take the integral, the sum of all of the little pieces times all of the different radiuses. And then you get the moment of inertia. So it's this, whatever, it's this complicated integral thing. And if you're a junior and you want to learn how to do that, take AP Physics C next year.
Oh my gosh.
If you don't want to do this, click. Happy joy, don't think about it anymore again in your life.
Mr. McClure,
Yeah.
go to your collars tucked into your sweater.
Why did you
Okay, cool, thanks. All right. Then, so here, do we see that if I know T, finding A is trivial?
No. What? No.
Because if I, look,
Oh, because 8.
Yeah. Right? Does that make sense? If I know t, I just plug it back in over here and I'll get a. And this is the acceleration of the string as it leaves the pulley. And then, of course, how do you get alpha from a? Anyone? Divide by r, thank you. So all I have to do is divide this by r and I get this. So this is this is like, let's say 6.5 newtons. And then, so that gives me 13 divided by the mass of the pulley, which was 3. 13 divided by 3 is like 4 point something.
4.3.
So that's 4.3 meters per second squared. And then 4.3 divided by, what is the radius? 0.12?
Yeah.
So divide 4.3 by 0.12, that should be like 1/8, so it should be like 32 or 33 or something like that.
It's 35.
35, okay. So we get 35 radians per second squared. Yes? All right, turn it off.